Hello everyone. The topic I will be sharing today is longitudinal decision making or wheel use in autonomous driving, which was a key focus during my internship. My presentation will be more engineering oriented and practical rather than deeply academic. Now, let's get started. From the title, we can notice two key terms: longitudinal decision making and wheel use. So, what is longitudinal decision making? Longitudinal decision making is in planning the vehicle's speed and acceleration along its intended path. The ultimate output falls into two primary categories: yield, yield and overtake. As illustrated in the diagram, if the AV allows the pedestrians to proceed first, this action is classified as yield. Conversely, if the AV passes before the pedestrian, it's categorized as an overtake. Why it is necessary to separate the decision-making for wheel use and vehicle. Wheel use included pedestrians, cyclists, motorcyclists, and the other non-motorized road users. The main reason is that their behavior is often unpredictable or it's really hard to predict it accurately. Before introducing longitudinal decision making, let's recap the autonomous driving pipeline. In an autonomous driving system, perception and localization are upstream processes while decision making is downstream. Decision making follows a sequence of lateral decision making, lateral planning, longitudinal decision making, and longitudinal planning. Lateral decision making determines which the AV should get. Lateral planning generates the path. Longitudinal decision making then determines the speed and acceleration based on the path, which is implemented by longitudinal planning. This is the final trajectory. So, how we approach longitudinal decision? The conventional method is as follows. First, based on the path generated by lateral planning, transform this is path. Transform the Cartesian coordinate system into a Faraday coordinate system. Next, project the predicted trajectory of VRU onto the ST graph. The methods such as A-star or dynamic programming study to find in ST graph and carve out convex space. The yellow patches is the convex space. The convex space serves as one of the solution space for longitudinal planning. However, the issue is that, as mentioned before, predicting wheel use behavior is very challenging. And those methods is maybe useful for vehicles, but for wheel use, implementing longitudinal decision making as in those methods maybe is maybe you should rely on entirely on predictive information for wheel use, which could lead to decision failure. Additionally, due to the characteristic of certain algorithms like A-star, those decisions may become overly conservative or aggressive. Therefore, further refinement of longitudinal decision fair use is necessary. Therefore, we adopt the following strategy. Initially, we use the traditional approach of drawing A star for longitudinal decision making. The result serves as a reference for longitudinal, or just act as a fallback when those decisions fail. Next, we partially trust the prediction results for value and label them based on the interactions between value and AV, as true in the figure. If the passes of values and the ego vehicle may have overlap, based on the order of arrival or collision situation, they can be categorized into labels, such as ego first, value first, collision. The value collide with ego first front part or collide with back part. Or in these situations may be labeled as ignore. The decisions are then made by combining these labels and with the A star results. Additionally, to refine the decision-making process further, yield and overtake are divided into quotient yield and normal yield. Caution overtake and overtaking norm. Those, yeah, those measures can refine the solving spaces for longitudinal planning. In practical, the classification will be more complex, but here I present only a coarse categorization. After obtaining the A star result and the label tag, we make a longitudinal based on different scenarios. One core aspect is when value first and the collision occurs, we perform sampling method to handle the situation. This is reflect our discharge predicted result. The sampling method process is quite straightforward. We sample the acceleration of both AV and VRU at equal intervals over the next second, 2 seconds, and 4 seconds, constructing numerous trajectories for both. Subsequently, we prune the trajectories that do not meet jerk and velocity requirement. Finally, we connect all remaining AV and VRU trajectories to form trajectory pairs. After obtaining the trajectory pairs, we calculate the cost for each pair, which consists of comfort cost, collision cost, and road ride. Comfort cost is related to jerk, while collision cost depends on the distance between trajectory pairs. The calculation of road rides is as follows. First, we determine the time it takes for the AV to reach the overlap, and then calculate the distance between the values and the overlap area at the time. If values is far from the overlap area, like this, the equals road ride is 1. If the VRUs is within the overlap, the road ride or equal vehicles is 0. The intermediate region are interpolated between 0 and 1. Final calculated cost here is presents the probability of the AV yielding to values. The higher values indicate higher probability that AV should yield to failure. Additionally, we simultaneously calculate the risk value, which is the proportion of trajectory pairs that result in a collection. We make longitudinal decision makings by combining the yield rate, the risk rate, and also the A-star result. The illustration shows the approach described above can lead to more refined decision result, thereby obtaining a better solution space. Yeah, we can compare that the compacting solving space is here, so it will lead to a better planning result. However, as demonstrated, traditional methods I just presented above for decision making regarding to it's quite complicated, quite complicated, and also the setting of various conditions heavily rely on the practical experience. In contrast, end-to-end method is more appealing. As a company, where I intern, end-to-end methods have already been applied to lateral decision planning, generates policies based on the perceptions, while traditional methods serve only safeguards and enhancement. Consequently, end-to-end methods will eventually be graduated adopted for entire decision-making in module. From the current industrial applications, it is evident that C-labs and development hold significant potential and prospects. The ball is my understanding of longitudinal decision making and work I did during my internship. Thank you for all your listening.